Okay, so let's continue our exploration of alkyne chemistry. Let's look at hydration mechanisms. Now we saw with the alkenes, you can do a hydration of an alkene using mercury and water, or mercury and acid. So maybe we can do the same thing here, only it's slightly different. Now we are catalyzed by mercury. So we're going to use the mercury and we're going to get the mercury back. So it's a catalytic reaction. So that's interesting. So we have to use the catalyst, and before the mechanism's over, we have to get the catalyst back. That makes it catalytic, right? Remember, catalysts are not consumed in reactions. They're used in the mechanism, but they're not consumed. So that means you get them back, and they go and do the whole process again. So now we're going to put this in the presence of water, mercury sulfate, and sulfuric acid. So all these things are mixed together, and you get maybe something unexpected. You get a ketone. You do not get an alcohol. Well, you do. Let me explain. You do get an alcohol, but the alcohol goes to a ketone right away. You get what's known as an enol, and that converts to a ketone. We'll see that in a moment. Let's do the mechanism first, and then I'll explain keto-enol again. We've seen it in a previous unit, but we're going to take another look at it. All right, so in this reaction, we have mercury plus 2, or 2 plus. So of course, one of the pi bonds is going to be attracted to it and attack it. And that's going to give you this cation. Where now water will attack that cation. Now I'm going to warn you, this mechanism is going to be a little bit freaky from what you're used to seeing, but that's okay. That's all right. It's good to have new experiences, right? It's going to be a little bit hard to see at first, or a little bit challenging for you, probably. Don't let that deter you, though. All right, so the water attacked the carbocation, forming the protonated alcohol, which is now, of course, going to deprotonate. You've seen all this before. Nothing here is new to you. Okay, so then you get this enol-like structure. Okay, now, at this point, you get more acid will come in. Now at this point, the pi bond from the alkene will attack the acid. You've seen alkenes do this before. So this is not new. Alkenes definitely attack acids. And you put a cation on that carbon. That's not new. You've seen that before. That's nothing new to you guys. But now, this can resonate. Because the lone pair on the oxygen is going to stabilize that carbocation, right? Because carbocations are not good. They don't have octets. Now here's something that you haven't seen before. At this point, the electrons that are in this bond between carbon and mercury, at this point, these electrons can let go of the mercury So, and when they do that, of course, they reform the mercury plus 2, right? So right here, these electrons go into this to make a pi bond right here. That liberates this mercury as mercury plus 2. So the mercury is not a leaving group. The leaving group is actually this whole big thing here because it's taking the bond electrons with it. So this liberates the mercury as mercury plus 2. So the mercury plus 2 can go back up here, do the mechanism again. Now, of course, we can't stop here because we stop here, we're going to violate the octet rule. So the electrons from here go to form a lone pair. There you go. And this is enol. This is known as enol. Now, in order for me to explain the rest of this mechanism, as if it's not hard enough, right? We need to understand what's called enol-ketyl tautomerization. Enol has an alcohol directly attached to an alkene. That's why they're called enols. Enols are unstable. They would rather go back to being, or rather go towards being what's called keto. And these reactions are oftentimes acid catalyzed. They can be base catalyzed too. Oftentimes they're acid catalyzed. So let's see what that looks like. So I'm going to draw my enol here. So I'm just going to redraw the enol that I had in a previous slide. There we go. So this is the enol that we had on the previous slide. Now, remember, we're in sulfuric acid, so there's lots of hydronium in here. So again, the double bond attacks hydronium. You've seen that happen before. Double bonds protonate. They do that. No problem. That should not freak you out. It forms the cation there, which now will resonate to give you the protonated ketone. Which water will deprotonate to give you the final product, the ketone. And there's the final product. So that's the mechanism of how mercury can catalyze the hydration of an alkyne. Now, you thought you'd see an alcohol, and you did. There's the alcohol it forms right there. But what you learned today, and what's new for today, is that you saw, okay, this is an alcohol, but it's actually not just an alcohol. It's an enol. There's a double bond right here. So this tautomerizes to give you that, the ketone product. Okay? So that's the Markovnikov addition of a water to an alkyne. Of course, we have to look at the anti-Markovnikov version. So let's take it let's take a look at the hydroboration-oxidation of an alkyne. Or SIA. It's called a secondary isoamyl. So that essentially SIA, I want you to think of it, you don't necessarily have to remember the structure. I want you to think of it as bulk. It's just bulk, big stuff, okay? So far, basically the setup for hydroboration oxidation of an alkyne, similar to an alkene. Alkene, we would have just used BH3 here. Alkynes, we use this secondary isoamyl borohydride borane, because we want to have this bulk here. We want to force the boron to add to this carbon only, not get any kind of mixtures. Because all this bulk is here, it'll help to guide it away from this R group. It'll help us direct the oxidation. And in this product, in this mechanism, you will get an aldehyde. Now, from a hydroboration oxidation of a pi bond, you expect to get an alcohol. And we are going to get an alcohol here. We are. It's going to be enol. Just like in mercury hydration, you're going to get an enol, which is going to tautomerize to a keto. Or in this case, it'll be an aldehyde. All right, so let's take a look at the mechanism. Very, very similar to what you already know. Let's put a little box around this guy. There we go. So very similar to what you already know. You already know that pi bonds are reactive to boron. There's nothing really new here. So the boron and the hydrogen from the boron add in a syn fashion. So that's the first step, and you guys already knew that. You saw that in alkene chemistry. Then, and this you guys have already seen the next step also in alkene chemistry. Basic peroxide gets deprotonated by hydroxide. And you get the anion. Which then will attack the boron. And just like in alkene chemistry, at this point, we don't have to know the mechanism. There you have it. And that will fall apart to give us our alcohol. But again, it's not just alcohol. It's enol. So that's not the product. Oops, I guess I went a little bit below the screen there, didn't I? So this is not the product. It's not. This is a tautomer of the product. So let's see how that looks. So let's see how that looks. Now we have the enol tautomer, right? And don't forget, we're in base. We're in basic peroxide, so there's base here. Oops, let me make that red. So don't forget, there's OH minus hydroxide floating around in here. So that will attack the hydrogen, giving you the anion, the alkoxide again. No problem. Nothing new there. Which, of course, this can resonate. Now we're starting to see it, I think. I think everyone's starting to see it now. Oops, 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 oops. There you have it. Now next, the water. Will protonate the carbon, and that will generate the aldehyde. I'm just going to flip it over so that the carbonyl is pointing up, as it's traditionally done. And there it is. There's the aldehyde that we generate in this reaction. And this is the mechanism of how it works. So it bears a lot of similarity to alkene chemistry. And then there's a ketone enol tautomerization going on there. Not a problem. This is how it works. Okay. So remember, enols are generally speaking not stable. They tautomerize right over to the keto very, very rapidly. But the enol does exist. It's just a very, very low concentration at equilibrium. So this is the predominant tautomer for sure.